I'm Liuba Shrira, and I will talk about some. The introduction was really great that you heard, and I will talk about a little bit about some of the issues that arise in transactional memory. If you work with pure transactional memory, software transactional memory, actually. So, transactional memory, so one of the issues sort of that arise in software transactional memory is, imagine the following situation. Let me talk about example. So you have a red and blue thread, and the threads need a unique ID. Maybe because they need a key to stick it into, they generate elements and they want to stick them into a set, and they need a unique ID for each, unique key for each element. And they use, a counter to generate unique IDs. So there is this, in a non-transactional case, there is no problem. Somewhere, one thread asks for a unique ID. If a concurrent thread asks for a unique ID as well, there is some synchronization underneath, probably fetch and add or some other atomic operation. One of them gets an ID and another gets an ID. No problem. Right? This is a standard situation. Now, assume that you are now in a transactional memory case, and so each thread actually runs, a bunch of operations, and among them, but each operation, each sort of thread runs essentially a transaction with begin transaction, end transaction, and somewhere in the middle of that transaction, they need to get that unique ID to put it into the elements that they're going to stick in somewhere. Well, now, exactly the same situation, but here one thread asks for a unique ID, got something, keeps working on, and then the other thread also asks for a unique ID, a concurrent thread, but now one of them cannot complete. Because what happened, whoever went first read the counter, initial value of the counter, and then by the time they came to commit, the other thread already got another value of the counter, so the counter value has advanced. So when the transactional memory is validating the first transaction, that transaction has a conflict, right? So it aborts. Everybody with me? Right, this was explained. So transaction aborts, that's the gain. However, if there is contention and you have many transactions, you basically are stuck there, right? Running again and again, and you cannot make progress. So really, whose problem is it? It's not really a problem of STM, because as far as STM is concerned, reads and writes conflict, and so two transactions have a write. If you're talking about a counter, they access this integer counter, and the counter operations conflict, read and write conflict. So STM is fine. However, a programmer really understands that there is really no conflict semantic between two unique IDs. It doesn't really matter if you look at the unique ID data structure that provides unique IDs. It doesn't really matter in what order they're assigned. You can reorder them, it would still be okay. They don't truly conflict. And so the question is, what to do about that? So this problem that where developer understands that certain operations could be done in any order, it's clear to the developer, but the STM doesn't let them to complete in any order because there is underlying read-write conflict. This problem actually was bothering STM people who develop on STM for a long while, and anybody who studied sort of the history and looked at techniques proposed has seen a variety of proposals. So the proposals, probably you have seen something called relaxed atomicity, where people say, oh, let's not do exactly atomicity. It's okay to do something which is weaker, or you may have seen early release, which says, well, those locations, you don't really need to check them. Why don't you remove them from the read set and do something else, ignore them? Or sometimes maybe you have seen open-nested proposals. So there has been a bunch of proposals. It's really frustrating for the developer because the transactions conflict for no good reason, right? And so there is a bunch of techniques trying to adapt to avoid the conflict. This problem is actually, how many people did databases here? Took a database class? Probably many. So anybody who took database class, sort of classical, probably starts sensing that there is something sort of similar arises in databases. And databases have done a lot of work, and there it goes under the name of type-specific concurrency control, where the concurrency control takes advantage of the type of the operations that are being, like for example, counter operations, really can be done in any order, but words, reads and writes are conflicting. So the question is, can we use those ideas? Turns out that databases really have lots of interesting ideas. Those ideas all are based on exploiting commutativity of operations and non-determinism. So non-determinism and commutativity of a data type operations is actually what is being used in databases. Turns out that databases, transactional memories are somewhat different, and I want to kind of zoom and understand exactly how transactional memory is different that way and what's special there. Okay, so I don't know how many if you heard about escrow. That's one of the examples of the techniques used in databases. They're all sort of similar, but not quite. There was exoleasing, some work that we did a while ago. All right, so TM is a bit different. So the key issue is here that no proper distinction is made between thread-level synchronization and transaction-level synchronization. These are not the same, and that's what I would like to do. If there is one thing that you take out of this lecture is the distinction between thread-level, low-level synchronization and high-level transaction synchronization. And if that distinction is made and understood well, we can do much better. So, yes? So actually I will talk about, so what I mean by commutativity is, in general, commutativity of operation just means that if you have two operations, you can reorder them, and the effect, they produce the same effects, meaning the value is the same of the operation, and the object is left in the same state. So we say operations commute. I will be a bit more precise when I get it there, but it doesn't. So, for example, in unique ID, giving two IDs to two threads is a commutative, those two operations commute. Because if you think about generating keys for two elements, two threads can get distinct key. The only property that a unique ID generator guarantees is that those are unique IDs. They're not ordered in any way. They just have to be unique. So two operations that produce unique IDs commute, right? They leave the system in the same state. No future operation will observe the difference, and so the object state is the same, and also the results, the outcomes of the operations themselves are the same. So they commute. But two integer counter values, which can be observed, they do not commute, right? Obviously. It's like standing in line, getting a ticket, right? It's not the same being first and not first. Okay, so yes, please feel free to ask questions actually at any moment in the middle. It's better to ask them right away rather than wait as we go if something is unclear. So the difference between sort of thread level and transaction level synchronization is at the heart of the problem. And if you confuse them, then that's where the concurrency gets killed. And so all those models that I was mentioning that do relaxed consistency, they actually combine the transaction level and the low-level thread synchronization together. So you're just really undermining the concurrency. So if transactions only look at read-write synchronization, if they only use for synchronization read-write conflicts, we have no hope of scaling. Because that essentially means that all the work that people, like Nir was describing to you, all those fancy data structures that can be highly concurrent, all the work in Java concurrency library, you cannot use them. Because if you run them on top of STM, the knowledge about the concurrency that the people who implemented those data structures, their fancy operations, they're invisible to the transactional memory, right? They see just read-write conflicts. So what I want to talk about in the rest of the talk is how to actually take advantage of those highly concurrent, clever data structures that people have designed, that the Java concurrency library is full of them, in transactions. So for example, if I have, 2 trees and I want to transfer elements from one tree to another, that's my transaction. And the tree is a highly concurrent tree that I pulled from Java library. I would like to be able to synchronize my transactions, not if those operations are accessing sort of independent parts of the tree. I would like to be able to, my transactions to commit. They really don't conflict. A highly concurrent data structure allows you to do that, right? A highly concurrent tree will allow 2 inserts, for example, that don't affect each other because they do different keys to proceed concurrently. There is really no conflict between them. That's what highly concurrent data structures allow you to do. And so I wanted to show you how to take advantage of those highly concurrent data structures in transactions. So basically, I will talk about 2 ways to do that. One way is very appealing in a sense that we just buy the highly concurrent data structure as a black box and use it as is. But there are some restrictions on use of it. And then the other one is sort of, that's full code reuse, right? So somebody sold you this latest and greatest data structure, you just use it in a transaction as is, plus some infrastructure. The other approach is, requires more work. It actually requires you to open the box and adapt the data structure to transactional framework, but you can get better performance. So 2 ways. So yes, so again, we make a distinction between short level, fine-grained synchronization implement it using, for example, test and set or fetch and add or one of those atomic operations, maybe hardware transactions. Short critical sections. This is what is used to implement those highly concurrent data structures like queues, skip lists, trees, hash tables, all the things that programmers pull out of Java concurrent library when they want to use it in multi-core environment. And long-lived, coarse-grained transactions that are used, for example, you can use them for moving elements from a tree into a hash table or do multiple operations, application level transactions that use those data structures, right? So we have this short-lived, fast, fine-grained atomic sections for data structures and long transactions. And what we want is we want to take advantage in the long transactions of the data structures. So the first method, called transactional boosting, is essentially a way to transform, using black box approach, a linearizable data structure, highly concurrent object, into transactional object. So you can use it in a transaction safely and get there essentially as much concurrency as the data structure allows. So let's look at the first, talk about data structures, about those linearizable, highly concurrent data structures. So here is a data structure. Here is my concurrent object. This concurrent object is a queue. Time goes from left to right. In a queue, linearizability means that this execution is equivalent to serial execution where every operation happened instantaneously. So here, in this specific execution, NQ, one transaction, the blue one, did an NQ X, and then after that, the red transaction did an NQY, and then the red transaction dequeued. Since NQX happened first, it dequeued X, and then when the blue transaction dequeued, it got a Y. Right? So this is a linearizable execution. This, even though the transactions were running concurrently, the data structure linearized the execution. The result of the highly concurrent data structure is equivalent to linearizable execution. That's what the data structure guarantees. So the synchronization that was used for this data structure is what I call thread-level synchronization, right? Threads come in, and the data structure synchronizes the data structure operations. NQ, dequeue. If it was a tree, it was insert, remove, add, lookup, right? Or other data structures. Those are what I call, from now on, thread-level synchronization. Transaction-level synchronization happens above. It synchronizes operations of the data structure, right? They are not the same level. I want to really distinguish them. So, for example, in a runtime, we want to sort of disentangle them. We want to speak about them in a different, like as if in a different language. So what you have is a library. And in the library, we will have, underneath we have those data structures. And in the library, we're going to have abstract locks and logs of inverse operations, and they are going to be used with the operations of the low level. So underneath, you will have your favorite data structures. The higher level operations, the higher level synchronization will be based on commutativity of the lower level operations. So let me give you just an intuition how the scheme will work. So the idea is, say underneath you had a set operation, a set data structure. Some operations commute offset and some do not. If operations commute, like for example, insert an X and insert a Y and they're not equal, then our library is going to let them go concurrently. If the operations, however, conflict, meaning insert of X and remove of X, they do not commute. Our library is going to use locks and prevent one of them from going forward. So it's going to really serialize them. It's going to block one and allow the other. So operations that are commutative, that can be run concurrently from the point of view of transactions, will be allowed to proceed concurrently without conflicts. And the abstract locks in the library, I will be using the abstract locks to actually lock operations. Right? So my library, the designer of the transactional data structure for the library is going to look at the specification of the data type and is going to have to figure out which operations commute. A specification typically will tell you which operations commute. And it's going to assign a lock for operation, different locks, conflicting locks for operations that do not commute. And it will allow compatible locks for operations that do commute. Now, if I have a transaction and it may access many operations and transactions go forward, concurrent, they will use my underlying data structure to insert elements. What if transaction aborts? If transaction aborts, I have to erase the effects. My library cannot put fingers inside the data structure. The data structure is abstract, right? It's a black box. So anytime during a transaction, I invoke an operation, my library will have to log an inverse operation. An operation that if the transaction aborts, it can do an action that will erase the effect. So for example, I will look in a moment in more detail at the code, but in general, if I insert X, I have to log and remove a delete operation for X in case the transaction aborts. Is the intuition anyway clear? Okay, so yes. So just stop here and I'm going to use a data structure, right? Like your favorite data structure for Java concurrency library. So the way to think about it right now, forget for a second about STM. Just think about Java concurrency library that runs on top of memory and allows highly concurrent has highly concurrent data structures. This technique will work on the side of a STM. Things that don't use highly concurrent data structures will use STM. And this part will use the data structures, because data structures will allow you to take advantage of the extra concurrency provided by the data structures, right? So, okay, so let's look, so any of the book, any data structure from the book, you were able to sort of take advantage in the method. So what you need, as I said, you need commutativity and inverses. You need to know which operations of a data structure commute, and each operation that you're going to invoke has to have an inverse in case transaction aborts, so you can undo the effects. And with those two tools in hand, you should be able to use boosting. So, for example, let's look here. Let's say you have a tree, right? And you have a red thread who wants to do an add operation to a tree. So it adds an X. It's going to grab a lock. The library will allow you to grab a lock. The lock is on abstract X. So that if another thread comes and wants to either add an X or remove an X, they will have to be blocked. But if another thread comes and it wants to add a Y, it's going to use a different lock. They will not conflict. So we need an add. When thread that issues an add operation, it also has to supply a remove operation. It has to log in memory a remove operation, so that if the thread at the end ends up aborting, we can call, the system library is going to call remove and undo the add. Because you have to undo, abort has to erase all the effects of the operation. So you need undo log, so that your transactions need undo logs and abstract logs. Those are the two mechanisms that you are relying on to use with your black box object. Now, so let's look at some code, because maybe that will make it more concrete. So let's say I have a transactional set. I have a set. My set is implemented. I'm going to use for my set, I looked at Java library, there is concurrent skip list. Skip list is great for a set. The operations are logarithmic, so it's a good data structure. It's highly concurrent. But the library concurrent set cannot be used in transactions, right? So I'm going to use this boosting technique that I kind of vaguely described to you to transform my concurrent list from Java library into transactional list. So my transaction, for example, can do have two lists. It can do begin transaction, take element from one list, put it in another, and then commit. And as long as 2 transactions, or 10 transactions, or 100 transactions run on this concurrently and access different elements, they will not conflict. So, as I said, the first thing we need to do, we need to look at the specification of set. Because the first thing we need to do is to figure out which operations conflict. So here I have my operations, and I mark them together with a reply. So there is a the notation is add X and then the reply, because sometimes commutativity depends on the return value. So here is an add X operation that returns false. It returns false if the operation if X was already in the set. So because I need for every operation an inverse, I'm specifying on the right what is an inverse for this operation. So an inverse for a add x operation, if x was already in the set, is no-op. I don't have to do anything. The operation had no effect, right? So an inverse is no-op. Add x that returns true actually modifies the set. So an operation add x that modifies the set, its inverse has to remove that x, right? So the inverse operation for add x true is remove x true. Yes, everybody's with me? Operation remove when an element, yes. Yes. Not right away. I am preparing myself for a bad day where my transaction aborts. If my transaction aborts, right, transaction may have hundreds of operations. If I insert an element at the beginning using the data structure, right, the concurrent skip list, and then sometimes midway turns out that there is some problem and my transaction has to abort. My element is already in the set. I just inserted it. I have to undo. They are not going to look because I am going to log them out. The somebody is another operation that does not commute. An operation that could observe my effects of my insert, X, and be affected by that. It's an operation that does not commute by definition with add. So I have to prevent it from going forward, right? I'm going to lock it out. It is about locking plus inverses, right? So it's locking and inverses. So far, no transaction memory. So remember, our problem was the following, just to remind what problem we are solving. If I took the same data structure, skip list, and I run it on top of transactional memory, I get no concurrency. Why don't I get concurrency? Because it's enough that the data structure increments some counter, benevolent counter that counts the number of operations. All transactions will conflict because all of them increment that counter. But really, conceptually, the developer knows that increment the counter doesn't really, this is not really a conflict, right? It's a benevolent operation. Does that make sense? Okay, so I'm painstakingly went over the specification, right, and convinced myself that I have for every operation that the data structure provides for add, remove, and contains. The data structure also provides me with I can use a data structure to specify an inverse, right? Yes. So we're going to, in a moment, see how, but that's a very good question. You and I decide whom we are going to lock. So how do I know whom to lock and whom not to lock? So now I'm thinking, which operations conflict here, right? So let's look. This already specifies your conflict relationship as well. The commutativity is part of the specification. It tells you which operations commute and which ones don't. The ones that commute are marked with two arrow that goes both ways. And if it doesn't commute, then there is a cross out. So insert X and insert Y, right? Commute as long as X not equal Y, right? So two inserts commute as long as they don't insert the same element. Two adds, right, don't commute. Two inserts, sorry. Two removes also commute as long as x not equal y. And insert and remove commute as long as they x and y are not the same. So I don't need to exclude those operations. I can let them go forward concurrently. However, add x, add x that adds to a set that already has an operation, commutes also with contains x, right? Because add x false doesn't do anything, and contains doesn't do anything either. Those are two observers. So they commute. They don't have to exclude each other. And similarly, remove that removes, if an element was not there, commutes with contains. Both of them are observers. They don't really do anything. So they can go forward. All other operations don't commute. So I have to exclude them. Yes. Any questions? Yes. Here is an implementation. I'm showing you how it's implemented, right? So if you look underneath, right, here is an implementation using boosting approach of a transactional add using the concurrent skip data structure. So the first thing that I do, right, so my data structure here is a list of integers in a skip list. Right? For simplicity, it's integers. And I will have a lock data type, and the lock data type is the abstract lock that I was telling I need. And I'm going to show you how I implement it. Let's assume for a second that I already implemented, right? So the operation add, the transactional operation add v, the first thing that is going to do is going to grab a lock. And the lock is going to pass v. Its lock class responsibility to lock only the needed operations. I'm going to show you the lock class in the moment. It will be a hash table of locks, so nothing fancy. And it will be a lock for every operation that does per v. So just kind of to make sure that there is no mystery there. And now, after I have the lock, I'm invoking an operation on my skip list, right? So I am doing list add v. And now I'm going to get back a result. So answer to your question is, how do I know what is the result? Well, I just called it. Very good. Excellent question. So what you're saying that my implementation, the specification allows more concurrency, more commutativity than my implementation takes advantage of, right? My implementation is a bit naive. Two operations add into a set that already has an element, two x's actually commute because they didn't do anything. But my implementation is going to block them. But the boosting approach doesn't tell you to use up, squeeze out every single commutativity of operation. It allows you to most easily, you could design an implementation, I bet if you spend lots of time, it would be complex to squeeze out more concurrency, right? But I'm showing you a naive implementation that works for practical purposes, gives you that. But that's a very good observation. You're saying, the specification allows me more concurrency. I'm saying, fine, let's live with that. Does that make sense? I'm showing you to come up with what? I am with you. I have no idea. I don't know how to implement it. But what I'm saying that this is, a corner case. I'm showing you how to get more concurrency. But it's a very good question. The specifications can allow much more concurrency than we can take advantage. But I'm competing with the STM. Right? The STM has no clue. It will definitely not let you proceed concurrently with those operations because the operations at the bottom will going to conflict on a counter. Right? Okay, so so I locked it, and now if the result, if the element was already there, let's say the element was already there, so I didn't do anything. The operation add is a no-op. Then I don't even need to create an inverse. There is nothing to do. So I will just return the result and that's it. However, if my list add v was successful, in other words, I really inserted the element in the set, I have to prepare an inverse operation so that if this transaction that calls the add, if it aborts, I better remove the element from the set because the transaction has to leave no effects when it aborts. So that's why if you look at the, if the result was true, in other words, if add operation succeeded, I am creating an on-abort an exception handler that is going to call remove v. If I asked you now, this is all about for how I get a transactional add operation. If I asked you now to implement a transactional remove, I bet you know how to write it, right? You simply replace here add with remove. The inverse will be inverse of, on top of you will have a remove, and then the inverse will be add. Really symmetrical implementation. Yes? Very good question. Somebody's not sleeping after lunch. It's the transactional library that is going to release all the locks at the end of the transaction. Because if transaction aborts, the transaction library is going to invoke the undo operation that I logged under the protection of this lock that I'm holding. So then it will release the lock at the end, right? So it's, yes. There are numbers, but I don't have them. I have, my competition is STM. So I am showing you how to compare this contraption with STM. Now, it's a very good question, how much penalty we get. And in fact, we do some penalty, get a penalty. But the point is that you could not use a regular concurrent skip list in a transaction. Your transaction would abort every time. Right? Yes. Did you ask why wouldn't we deadlock? So I think you can probably deadlock. And what's nice about transactional systems, and this, every database knows, if you deadlock, you just abort the entire thing and start anew. This is a cop-out. I didn't mean to say there are better ways and there are techniques that do better, but I'm just saying all database essentially systems, deadlock detection is a very expensive proposition. So if you get into the kind of a timeout situation, you're usually driven by timeouts and they just abort after a while. Okay, so let me just show you the lock key because I want to get to the other method. So to wave my hands through. So this is the lock. This is the implementation of the abstract lock service, so to speak. And what it is, it's a hash table. And in the hash table, there will be a lock for every key. right? That's it. And the hash table itself is a hash table from Java concurrency library. So it's a highly concurrent hash table. It's a shared hash table, right? Because all threads need to get to the... okay, so I'm trying to... Here is my map. The map is concurrent hash table, and I'm creating a hash table, and then I'm showing you how a lock operation works. So I pass it the key, and the first thing it does, it needs to know whether the key already exists, a lock for that key. So it's going to check in the data structure, in the hash table, if the lock is there. So if the lock, if it returns null, it means the lock was already there. So then I have to check. Let me just talk you through. I have to check if I am the one who is holding that lock. If I am the one who is holding the lock, no problem. If somebody else is holding, some other thread is going to holding that lock, I will have to wait. In any case, a thread has a local set where it keeps all the locks, all the abstract locks it has acquired, right? That's what will be released at the end of a transaction of that thread. So, if the lock is null, right, then I'm creating, if I'm creating a new lock, and then I'm trying to check if the lock is already there, and I have to figure out if it's a new lock or it's an old lock, and if it's in other words, if it's my lock or somebody else's. But I have worrying that another thread, after I got my lock, another thread may stick in the lock in the meantime, right? This is a concurrent hash table. It allows other. So I check if between when I created my new reentrancy lock and when I'm trying to add it, somebody else inserted it. So this is a check if my lock, right, the lock set add, if the lock that I inserted and the one that I have, it is the same. If it is not the same, means somebody else inserted the lock, and I will have to wait on that lock. So I figure out which lock it is. So now my lock is either the old or the new, and now I'm trying to check if I have my lock, if I am the one that has the lock. Just 1 second. If I am the one who has the lock, if I have the lock, then I really don't, I just need to, I have it and I am done. If I don't, really, it's not in my set yet, I have to acquire it, and so I'm doing try lock with a timeout. I'm waiting. If I cannot get the lock, I will abort, right? And transaction will abort, and I will try to do it again. Yes?